So in the final part of Module 4, we are going to apply bit commitment schemes to proofs of zero knowledge. The fact that you have a bit commitment scheme is a very powerful primitive which allows you to create many proofs of zero knowledge, protocols for zero knowledge. I'm going to show you for the Hamiltonian circuit. Remember, a Hamiltonian circuit, you have a graph and you want to know if there exists a circuit, which means there is a path that goes through every vertex exactly one, and that gets back to the initial point. And it's interesting to know that Hamiltonian circuit is an NP-complete problem. I'm going to show you the protocol only using a toy example. It will be very clear how to generalize it. So we suppose that we denote the graph using its incidence matrix. So I give you this example here. It does have a Hamiltonian circuit. And what we are going to do now is the following. The overall structure of this protocol is this. We are going to create a permuted instance of G, which we are going to call H, and then we're going to commit to it. I'll give the details later on. But then we send the committed permuted instance, we send it to the verifier. Now the verifier is going to flip a coin, 0 or 1, and if the coin is 0, then the prover must show that the permuted instance was indeed created correctly. If the coin is 1, then the prover must show that the permuted instance also has a Hamiltonian circuit. So that's the overall idea. This is a very general construction. So detailing step 1. We're going to assume that the prover creates a random permutation on a set of vertices. So I gave this example here. This is a permutation between the 6 vertices. And so it will apply this to the graph, and this will give us an isomorphic graph, which is called the H. Okay, and then you must apply this to the incidence matrix, which is done here, and you're going to commit to each entry of this incidence matrix. So this is the commitment on H. Those are the commitment on the alternative graph is a commitment to each of the entries of the incidence matrix. So this is what the prover is going to send to the verifier. Now the verifier is going to flip a coin, as I explained, and if the prover gets to see the challenge, the challenge, if it's 0, then it's going to open each entry of this commitment here. So it's going to open all of this and show the permutation also. And the verifier will check that indeed H was a faithful copy of G. In the second case, this is the interesting case, if the challenge is 1, then the prover will show that the alternative version that it committed to has a Hamiltonian circuit. So it's going to open only those values in the matrix that show that there indeed is a circuit. So in this case, there's a circuit from 1 to 5, from 5 to 2, from 2 to 6, from 6 to 4, from 4 to 3, and from 3 to 1. So this shows, by showing these ones, and there's a 1 in each row and each column exactly, this shows exactly that there is a Hamiltonian circuit in the graph. And I'm not going to do this for you, but you must think about the properties that we want. Why is this protocol complete? Why is it sound? And why is it private? Why is it zero knowledge? And so we've seen a kind of common structure for these protocols, at least the protocols that use bit commitment. But also, if you think about the discrete log protocol, you can think of this the gamma that was sent in that protocol as a pre-rooted instance, and then there's a challenge, and then there is like in the zero case, you're going to show that things were done honestly. In the second case, when C is 1, you're going to show that the desired property is satisfied. That this is a very common structure for the zero knowledge protocols. I want to mention that, so in the case, this is sort of a famous story to explain zero knowledge, Alibaba and the cave. There is a secret door, and the prover must show that it knows the key, and the verifier is going to tell the prover, oh, come by this way, oh, come by the other way. So there are two alternatives as a challenge. There's another famous one, is the Sudoku zero knowledge. I find it slightly more difficult to understand because there are 28 alternatives in that case as a challenge. There are like nine alternatives for 3 different properties, and you also need to verify the original encoding. I do find these examples somewhat confusing. There is the example of graph colorability, in which the number of alternatives, if I'm correct, is the number of edges that you have in the graph, and you have also the condition to get to a small probability is more complicated. It can also be applied to the Boolean circuit, in which there are 2 alternatives as a challenge. It's very similar to Hamiltonian Circuit, and we'll be doing it in the final part of this module. But first, I want to tell you about a terminology, about the difference between the word proof and the word argument. I told you earlier on that commitment schemes can be used of 2 different types. So one is that they are unconditionally binding and computationally hiding. And these were the ones that I constructed using RSA or using discrete log or something like that. So in that case, it's unconditionally binding, meaning that the prover is considered to be infinitely powerful, whereas the verifier is only polynomial time. And if you remember from my previous module about proofs, this is exactly the setting of Goldwasser, Micali, and Rakov when we talked about interactive proof systems. So this setting we consider as a proof. Now, if we invert the conditions of the binding and hiding of the commitment schemes, so these were the examples, for instance, with the hashing and with the Peterson commitments, then we have that the prover actually is polynomial time, and the verifier is infinitely powerful. And so these are meaningful protocol, but technically speaking, they are not proof systems, and to avoid any confusion, they are called argument. And the reason I'm mentioning is also this is what the A in SNARK stands for. I'm going to repeat the SNARK at the end of this lecture, but the A in SNARK stands for argument, the A and the R actually. So it means that the prover in this setting is polynomially powerful. So this is the distinction between proofs versus arguments.